So now we're going to look at some decay problems. So we've done this first at the bell ringer you should have done and some you do problems, and tried a couple of the problems on the first side of that worksheet to kind of get warmed up. And the next few things are are some examples with decay, but basically the same thing. Here's some links to some resources that are about carbon dating that are sort of interesting if you want to learn more about what that is all about. And next we're going to move on to a We Do Plus. So I suggest that you pause this video, read the question, and attempt to answer it. It's just slightly different, but same basic concepts. Follow the guiding questions. And then play the video in order to check and see if you got it correct. So the problem says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. Number 1. In 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by Arab Bedouin herdsmen. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. So annotating this text, I want to pull out the important information, which is the amount of years that need to go by for half the original amount of carbon-14 to be left. That's going to help us figure out what our decay rates are. Later on, they talk about a year that some jars were found, and they found that there's 76% of the original carbon-14. We're going to have to turn that into a decimal, just like we always do in math. Okay, so I have a little bit of information here, but what I really need to do is set up an equation with that first part of information. So they're talking about half the original amount is left for that amount of time. We're still going to be starting with our equation. So A equals A naught base E to the KT. So if we're talking about half the amount is left later on, I'm going to call A, our later amount, half, and I'm going to call A1 1. So it doesn't really matter what numbers I plug in, and they don't tell me how much, like how many grams or whatever of the carbon is left. I know that when I, do that division with A1, I'm gonna get 1/2. So I'm just picking some easy numbers here, and you can kind of just go with that. So then I'm gonna have base E, and then K I do not know, but I do know some time. They told me it takes 5,715 years for the decay to reach a halfway point from its original starting value. So given that we have all of that, now I'm going to be able to solve for K, just like we did before in those previous problems. So I'm going to kind of ignore the fact that we have 1 times E, and I'm going to stop writing that coefficient, but what I am going to do is take the natural log of both sides here. Okay, and what that's going to allow me to do when I start simplifying this, I'm going to come up over here. I have natural log of 1/2 on the left-hand side, and now I can use those properties of logs, in particular the power property, in order to bring that K times my year, 5,715, times ln of E, and I know that that's just going to be 1, so I can just sort of drop it from the expression. And the other thing that we can see here is that K is being multiplied by 5,715, so we can actually just divide by that number in order to find K. plugging that all into my calculator, here's what I get. I get that K is equal to, and here's what it says on my calculator, so I'm just going to write this down for you. 5, I'm going to round here, and then it says e to the -4. Alright, so that's an e right there. Let me just rewrite it here because it looks kind of goofy. So what does that mean? Well, that is in scientific notation. So what that really means is I need to move the decimal place 4 times. So I still have that negative 1, 2, 1, 2, 8, 5, 6. And I'm probably going to end up rounding that a little bit later on when I use it in my equation because I have a lot of decimals there. But the point now is that I have a K where I can use that in my equation to figure out how old these Dead Sea Scrolls are. So let's go ahead and do that. So basically, I know that my equation is going to be A equals some A naught times E, and now I have my K, so 0.0001213, we'll call it that, and then that's times T. So plugging in our numbers that we have, we know that 76% of the original amount is there. And remember that in math we always have to turn those into decimals. So my later amount is 0.76. And I'm going to call our A naught, I'm just going to call it 1. Okay, because that would represent like 100%. So the starting amount of carbon that a living thing generally has. Okay, so, or organic material. And then base E, and then negative 0.0001213 times time. And now what I can do is just take the natural log of both sides. That's going to let me use those properties. So I've got ln 0.76 equals negative 0.0001213 t. And remember, we still have ln of e, but that is only worth 1, so it just sort of, we can fade it away and not write it anymore. Okay, so the only thing left I have to do, and the only thing that's being done to the t, is it's being multiplied by that really small negative number. So we just have to divide by that. So I'm going to stick that into my calculator, and we'll see what we get here. And in the calculator, that gives me 2,262, and I'm just rounding to the nearest amount of years here. So that's years old. Alright, so we'll box that up for our final answer. So in this next you-do problem, on the slide that I gave you, I actually accidentally left out some essential information that you're going to need to write an equation for this exponential decay. So that essential information that's not on your slides that I just typed in here says use the fact that after 28 years a given amount of strontium-90 will have decayed to half the amount to find the exponential decay model. So you're going to need to use that information. 28 years is going to give you half of the original amount. So you're going to kind of set it up like we did with that you-do problem, and then just remember when you solve for k, since this is decay, your k value or your rate should be negative when you get that, and then continue on to make a prediction about how long it will take in order for the decay to reach 10 grams if you start with 60 grams.